Thank you. Yeah, a warm welcome from our side as well. To give you a quick idea of what this is all about, well, actually, we discovered this is quite a new area we are in now. And so during the preparations of our talk, we discovered that we actually want to talk, or the focus shifted a little bit, and we just at least wanted to reflect this here on the slides. So what we are actually talking about is how to do contracts right and how to work with contracts the right way.
So we'll start with a short introduction, then might give some, I think it's all news for most, but just a kind of recap of what we talk when we talk about event sourcing. Then we'll provide some introduction about how we see what kind of formal models we can use for event sourcing. This will lead us to the meat of this talk, which is about what is consumer-driven contract testing and what is there beyond CDCT. And then we might conclude by how you can put that in practice and what kind of takeaways you can get out of this talk.
Mm-hmm. Yeah, so for the introduction, why are we here?
Why are we here? I remember last year we were at the same conference in DDD Europe, and I met Nicole, and we had this fascinating discussion about functional programming and model designing and domain-driven designing. And we have kind of common interest in this kind of stuff, of course, because we are in the same conference, but with maybe a different perspective. At the time, Nicole was working a lot more into the front end, and I was doing a lot of back-end stuff. And then this idea grew that, hey, we keep talking about models, we keep talking about this kind of ubiquitous language that we're using, but we are siloing each other within our specialties, front-end, back-end, infrastructure, whatever. Would it not be interesting to find a way to have that kind of model that we are speaking about being reified and being used by everybody? This is not really new because kind of something which has already been done, but we'll try to find another approach and see if we can use that to make the different parts of the system beyond only the front end and the back end talk together. That was the idea of the talk, and that's where we stand now.
Yes. So, who are we? I'm Nicole. I'm a software developer, coach, trainer, you name it. What about you?
And so, yeah, I'm Arnaud. I'm basically also mostly software developer, and yeah, that's basically it.
Yeah. So, no big story.
So, what this talk is really about. And this is why the catchy title initially that we used is, could we find some intersection between domain-driven design, which you are here for, and formal methods? Basically, the idea of finding some kind of formal grounds for modeling what we are talking about. Hence the kind of mathematical, hand-wavy stuff that we are here.
Yeah, so we looked into this, and of course there are many seemingly overlapping areas, like domain-driven design talks about the ubiquitous language, formal methods also talk about languages. Then we have type systems where we describe things more closely, and then of course we have some good practices and techniques to get along with these. And yeah, we'll see where we get it. So, let's start out. Event sourcing. I think we are here at a DDD conference, so I will just skim over this very quickly. The ubiquitous language, as you know, it's ubiquitous. And what it does is it takes the terminology that the client uses into the code and also beyond. So, think databases or event store or whatever you have there. And yeah, we can finally understand each other using this domain, this ubiquitous language. And yeah, we also want to make it explicit. And then we also have commands and events. Commands are the things that come from the outside to our application or from some other system to the application that hit our application, like the user clicks a button because he wants to, I don't know, buy something or so. And then we have events, and those events are what the system then actually did in response to this command. So maybe it succeeded with the user interaction, maybe it failed. We can record this with events. And so if we look at all the events and just accumulate all the information that is in all the event history, then we get to our current state of the system.
So this picture summarizes the main ideas that we'll be talking about, the main concept we'll be using, which is, once again, some pretty much standard thing when we talk about event sourcing, is that we have this state, and we have the commands that produce new events out of the state, and the events modify the state of the system. And all this stuff is what we call pure. So for those of you who know about functional programming languages, we have this usual separation between what is pure and what is impure. Pure is pure computation, and impure is, well, stuff we are interested in, which is doing stuff in the real world. And the real world interacts with the system by sending it commands and persists the events. And so we have this kind of basic loop and basic interactions, or loops inside loops. The loop which updates the system and updates the state from the events, and the loop which updates and changes the real world by interacting with the system.
Sorry.
Yeah, go ahead.
First we thought we'd just explain this to you, but then we thought maybe have some practical example is even better. And so we came up with a online store where you can buy a pet if you want. And the first part that we're talking about here in this talk is the management of the store. So there is the store owner, and when he gets a new charge of pets, he can enter the pets into the system. And of course, if a customer buys a pet, then he can remove the pet from the system again. And then, of course, we have some of these obvious business rules, like you can't register a pet twice, and you can't remove a pet that's not there, for example.
So there will be a few slides with code in this session. I hope that the code is rather self-explanatory, but the idea that, well, this language, or these inputs, or as we call it, are pretty much straightforwardly transformed to code, where we say, okay, we can send a command which had a pet, we can send a command which removed the pet, and we have something else, which is the queries. So we can see already that there is our inputs into the system are already somehow classified, but from the point of view of the system, they are all inputs. But we can imagine that it would be interesting to distinguish between what is a command and what is a query. And then beyond the input, we have the outputs, and the outputs, the main ones we are interested in are the events for the store. So in this case of this store, we have two events corresponding to the fact of adding a pet and removing pet. So pet added and pet removed, and because those events represent something which has passed, something which happened in the real world, they are in the past tense, and we can have answers about the list of pets, and we can have some errors which happen to the system. And those errors are basically that, well, we are trying to add a pet that's already there, and we are trying to remove a pet that doesn't exist.
Okay. If there are any questions, please speak up at any time, and then we'll try to clarify things. Okay?
So, this is pretty informal, right? I mean, apart from the fact that it is grounded in code. So the idea is, this looks kind of similar with things that exist in the formal world, and most notably, conceptually, we can view event sourcing as a language. So that's the idea that we are trying to explore is that it is a language. This ubiquitous language is a language. It's a human language that is drawn from human experience through various techniques like, well, you know, event storming or work and interaction with real people. But what if we use the concept from formal language to actually put that model into something that could actually be implemented as a language? And so basically a language is, what is a language? It's an alphabet. So the alphabet in our language is made up of commands and events, which play some kind of symmetrical roles. What is a word? Well, a word is a sequence of letters, which is a valid sequence of letters from this alphabet, and the set of all possible words forms our language. Right. Pretty much formal language 101. And so this means that each word of the language we are defining here corresponds to a state of the system. And this is really the core idea of event sourcing and why it's really interesting and it's a really interesting technique and why it works, is that there is a direct correspondence between the language of the events that are produced by the system and that represent interaction in the system and represent change, and the state of the system. We can reconstruct the state of the system out of the sequence of events, and conversely, given any state, we can define and we can explore what events could have led to this state of the system. And okay, so back again to our small example, just to make things more grounded. What is the language of the pet store? Well, the language of the pet store, so we have represented here, I'm supposed to have a red dot, but
yeah, it's very, very...
Very faint?
Very faint,
okay, anyway. We have this starting state where we don't have any pets in the store, and then we have all the different states where we have pets in the store. And how do we add and remove pets? Well, we use the commands and the events that are in our state. And what's interesting here is that we can see the different roles that commands and events play. So for example, if I'm in the state marked P1 and I try to add pet P1, then the pets, the events that generated or the output that generated is an error, obviously. Because I can, by construction, that's part of the definition of my language and hence of my model. I cannot add a pet that's already in the system. And the same if I try to remove a pet that doesn't exist. Conversely, if I add a pet which is not there, then I move to another state and I change the state, right? So the thing is that with this, even with this very simple model, we can see that it's pretty much, infinite in no practical sense, because we can add more pets, we can remove more, we can interact in all various ways with the system. So that's the reason why there is this, those dashed arrows on the end. But conceptually, this is just a state machine, right? That's basically the model that we are trying to use and to define. And now that we have this model definition, the idea is that, okay, how to use that to make sure that when we have different parts of the system, like a front end and a back end, together, how do they talk to each other?
Yeah, and so first of all, we looked at how it's done in practice nowadays, and oh no, first, okay, what's the problem? We want to test that the front end and the back end play nicely together, whatever that means, right? So there needs to be some definition. Maybe it's implicit, but maybe it's better to make it explicit. So what we're currently facing is that getting a bit more into the domain-driven design language again. In the front end, no, I think it died. No. In the front end, we have commands, like somebody clicked something. And for example, with systems like Redux, we actually have something like events already there in the front end. And so we thought this is quite interesting because they somehow match the normal commands and events that you find in the backend if you think event sourcing. So what we discovered is that if the front end emits a command, then the front end already can turn this into an event. Maybe the event is only interesting for the front end. For example, there is a detailed box being unfolded or being closed. This is no event that the backend would be interested in, I guess, in most applications. But there are things that the backend would be interested in, like, for example, a customer wants to buy a pet. And we cannot turn this command into an event in the front end and then send this event to the back end because we don't know whether another customer already bought the pet, because the front end doesn't know about, like the other front ends maybe. Only the back end contains the real truth. So what the front end can only do is send its command as a command to the back end, and then the back end decides, oh, this becomes this event, and then this event, because this now is the truth for the whole system, will get sent back to the front end and then be registered there as an event, okay, to update the UI. And so what we already know is that if we stay in the front end and we just look at the command event loop in the front end, we can handle this easily. We can test this and we have everything under control. Same for the back end. But what happens with this in between, this funny gap there in the middle? We need to figure out how we can tackle this and how we can like fit these two parts together so that they understand each other, that they actually understand each other's commands and events. And yeah, we looked into the world and saw how things are handled in the real world. And there are a couple of approaches, and I will quickly go through them. The first approach that you can find is, let's call it super naive for now. You know, the backend just designs an API, and the front end will actually wait until the backend is done, and then the front end can, you know, work against the now completed backend. And you can also do all the tests and integration. Yeah, and this works very well because, you know, it takes it takes a very long time to actually finish something, because you can only do it one after the other. And also, as you probably all know, those integration tests running across front end and back end are not really nice in terms of runtime and in terms of maintenance and everything. Yes. So there's a better approach, but let's call it still quite naive. This better approach says, okay, the backend designs the API, and then the front end can actually specify a mock or write a mock that will then answer as if the backend was already done. And then the backend can be developed, and the front end can also be developed using this mock. Sounds like a better approach, but still, you know, the front end relies on these mocks, and as you all know, changes happen, so the backend behavior will change. The front end, of course, will not know because the mock doesn't magically change as well. So the front end gets developed against the outdated mock, and the back end just, you know, goes somewhere else, moves, its behavior moves, and, you know, you plug it together, big explosion. Very funny. Okay, so nowadays we have this industry strength approach, consumer-driven contract testing. Has anybody of you ever done this in like real life? Okay. Nobody? One hand. I see one hand. Okay.
I
Two.
see another half of a hand.
Another hand. Excellent. Okay, so very, very few people. Cool. So I will explain
Nobody
this.
has problems relating front ends to back ends, so maybe this is not a problem.
Yeah, maybe we... shall we go have a coffee? Okay. So how does this work? Consumer-driven contract testing. So we have a consumer, which is usually a front end, and we have a provider, which is usually called back end. It need not be that, but just for simplicity of speaking. Let's keep it that way. And we want to have a contract between those two parties so that both parties need to adhere to that contract. Okay? This is like the dream state. So now what we can do, and there are a couple of tools out there by now, what we can do is, given this contract that specifies how both sides should behave in working together, we can generate a stub for the front end, and the front end can then use this stub in development, or call it a mock or something like that, okay? We can also generate a bunch of tests out of the specification, and these tests can be used against the backend in development to check whether the backend still reacts according to the specification. And so now what happens if the backend deviates from the specification? The tests will fail. And in order to fix the tests, in order to adapt the tests to the new behavior of the backend, the contract needs to be adapted. And from that point, automatically, a new stub will be generated, or mock, for the front end to be run against. So the front end will automatically be made aware of those backend changes through the contract, and then through it running some tests against this mock, and the tests then failing. So then the the front end can again adapt to what the backend actually has modified in the contracts. Okay, makes sense so far? Cool, nobody shouts. So here we can see we have nicely divided those two areas, and they can be developed individually, but the contract keeps those two parts together. Here is an example that I wrote using a tool called Pact. So Pact like contract, sort of, like this, you know, with blood and everything. Here you can see, this is an example. At the top you can see there is a description, a request for all pets, and then we can specify sort of what should be the state of our backend be when we run this request. And here it's just a string, and we will see in a bit how this gets actually to life. This here says, I have no pets. And if I have no pets in the backend, and then I request the list of pets here through this API, then I'm supposed to get a response with a body that says, here are the pets, and the list is empty, because I have no pets in the backend, right? So, and running this test is fairly easy, because if you fire up a server that has no connection to a database or anything, then this will be like what happens naturally, right? So we have no pets, and then the test just gives us no pets, everything's great. But we also want to specify a bit more, I guess. For example, we want to specify the shape of the objects that we get back from the backend. And here I have the provider state, I have a list of pets. And this still is a string, right? And then I say, okay, if I now query the pets API, then I will get this list of pets, and there are 2 pets in it, and they have these and these data in them, okay? But we have not specified anywhere how this will happen, how the server will actually get to this state, so that if we query it, we will actually get this back. And this is one of the big problems I see with this approach, is that you actually, if you have a stateful backend, you have to manually, in your backend tests, have to manually provide a way of setting up the backend so that it can actually serve what you intend the contract to contain. And so there you have a bit of an entanglement here. And also, you write these contracts by hand. And this is the same as writing tests by hand. You only get a contract that is as good as you write it. And if you don't specify too much, or if you are missing out on certain critical aspects, then, well, bad luck, you know. So, and also, of course, this might be tedious to actually think about all these bits and pieces. Maybe you introduce some errors, and you only discover this quite late in the process because you just specify the behavior of the backend. And if you specify an error in there, and then later on, while you implement the backend, discover that the spec was wrong, then maybe the front end is already done, and then you still have this update across everything. And so, yeah. Yeah, I don't know. Maybe we can do better here. And yeah, so that's the point that we got to when we chatted together here last year. Is there anything we can do better to actually fix this and to actually, improve? We looked at existing systems, and there's especially one system which is called QuickCheck, which is quite famous in certain areas of software development. And yeah, we thought maybe we can borrow some ideas and thoughts from there.
So, well, consumer-driven contract testing is already a good thing to do. So that's something that really helps when developing distributed software and helps maintain the sanity of the development teams to a good level. We are looking for better. So back to formal language. If we have a formal language, if we have a state machine, then it doesn't take too long to imagine that. Well, if I have a formal language as a state machine, then maybe I could just do. Imagine that this would model the state of my system, and this models the interaction with my system. So the whole idea of using state machines to model system is quite obvious, right? What makes this interesting in our context is that it fits in very well with how event-sourced systems are designed and are implemented. The idea that we would like that we explored and then we would like to introduce you to now is really gets that verifiable model that define or describe the core domain interactions as a formally verifiable model, or at least as a formal model, or an executable specification, at least. Formally verifiable is something, it's kind of further goal, but we are not there yet, but at least executable. Something that we can run, something that we can run, and we can run deterministically. And given that that model, we want to do the two things that we are doing, that we have been doing with CDCTs, but in a much more structured way. We want to be able to generate mocks for the front end. So in this case, we will use the state machine as an acceptor. An acceptor in the formal language theory, an acceptor is something that takes a word and tells whether or not the word is part of the language. That's pretty easy because we know, okay, given a set of commands or inputs that are sent by the front end, are those commands or are those inputs legit? Are they valid with respect to my model? That's the acceptor part of the system. And that's pretty straightforward. Just follow the model. What's even more interesting is, given a model, then what I would like to do is generate tests for the backend and tests that represent the various interactions and that explore the state space of the model, just to be sure and to validate the fact that the backend itself implements correctly the model. And that's where we are using the state machine as a generator. So there is the real interesting thing is that just like in the case of contracts, we have the same thing that is used both as an acceptor to be checked and to check the front end, and as a generator to check the back end. And what we are trying to guarantee is that all aspects of the model will be covered by the tests and the mocks. So that's really a step beyond what we have been doing with manually written contracts. And this was actually, this is where actually the original title of this talk comes into play. I don't know if any of you is familiar with what is a homomorphism, but a homomorphism basically is just to say, if you have two languages, language A and language B. Then to define a transformation from A to B, it's enough to define a transformation from each letters of A to another letter of B, and that gives you a homomorphism, a transformation from the language of A to B. So two languages are homomorphic if there exists an homomorphism from the one to the other. The thing is that this transformation is transformation from letter to letter. So it's just like in our example in the contract driven in CDCT that we are just mapping one letter, one example, one thing. What we are mostly interested in is to be sure that not only are letters mapped to letters, and that if I send the command add a pet, then the command will be reflected in the backend. But I want to be sure that if I'm trying to repeatedly add a pet to my system, and if I violate any kind of business or any kind of rules of my domain, then this gets reflected in the front end, and this is also because this is implemented correctly in the backend. So you have this something which is much more dynamic than a simple mapping from letters to letters. So this figure summarizes everything. So what we do is that we have at the center we have our model, and what we do, we will check inputs from the front end. So we'll use the front end. So we will use whatever. The idea is to generate inputs from the front end using whatever tools you want, even manually if you want. So that, for example, for UI testing, that could be some manual interaction that we are trying to cover. And then what the model does is it validates the inputs and it generates valid output by construction because the model is the reference. And now on the other side, what we do is that we generate inputs from the model, and what we get back is checked again the model and check that it is valid. So we have this two-sided interaction, which is just the same that what we did with consumer-driven contract, but with a much more dynamic view. How does it look like in code? So here is an example. So we have used a simple model. So normally the rules should not be too complex. Forget the funny syntax. This is just Haskell. But the idea is that the pet store here just say, okay, when we add a pet and we have the state of the model, which is the store, then what can we do? Well, first thing, if the pet is not an element of the store, which is our basic premise, we can only add a pet, which is an element of the store. Then we just send the event, added pet, and we update the store. So we update the internal model. The internal state, so the state of the pet store here, which is just the state of the model, is something which is internal to the model. So it's something which is more or less abstract in the sense that we don't care whether or not it's a database or it's stored on disk or what's it's a model artifact, right? How it is practically implemented is irrelevant to the system. It's just a way to model the various states through which our system can go. And otherwise, we just throw an error. And we have a symmetrical rule or something similar for the remove part of the pet model. So it's very simple. And now, so given that very simple model, we can try to validate our front end and our back end. So this is where I will take the keyboard and try to show you how it works in practice. So here is our nice front end. So hopefully,
I think yeah.
So this is our nice front end. We have our pet store. We can add new pets. We can give a name to a pet, and we have different types of pets, right? And so I probably need to do something here to start my pet store. Doing demos during a talk is always something that makes me nervous. And now what I want to do is I want to test my store. but I want to test this against the mock model that I have just implemented, right?
Can you increase the font a little bit?
Yeah, I can do that.
Hope this is.
I can even enlarge the screen.
So on the right-hand side, this is just Webpack running the front end, so nothing special there.
And now what I can do is, what I will do is I will run my mock pet store on the other panel, and that will be a server. So this is just something that serves whatever I want to serve it. So if I refresh, now if I add something, I want, for example, to add a cat, and the cat has been added. And so you can see here that what my mock is doing is that it's receiving the command and sending the answers back. So there is, this is just the model running. So it's just a model running. And so far so good, so I can just add more pets. So if I try to add the cat and the time, so I get the error. And so I can test my front end that way. So I have a model of the system or a model of the business domain, even if the business domain of a pet store is not very, very deep. But whatever domain or whatever model I have, I can use that as a way to help me develop my component. It could be a front end, but it could be another service, of course. Front end is just something that's more graphic. So far, so good. So now I can do the converse with using the same model. So what I can do is I can now try to start my server. So I have written a small server in Haskell, which is an event-sourced server, which implements the pet store model. And now the idea is, OK, I want to test that my server actually implements my model. So to this, I will run the driver. So the driver is the part that takes the model and generates inputs and checks that the outputs are valid. I will redirect the outputs just to yeah, no, because I don't want to garble my screen.
Oh, OK, yes.
OK, so now what do I have? So I'm generating. So you can see here my server just dumped a bunch of logs, and what my driver did is the following. So what the driver does, just as explained before, is that it takes, it generates traces. So here we have the trace is something that says, OK, here is my starting state, here is the input, and here is the output that I expect in that state. That state is abstract. In sense, we don't display the full state of the store. We display an abstract state, which is a representation of a way to categorize the various states. And given that sequence, I can say whether or not the run is successful or whether or not it's failed. So here, what I can see is that, surprisingly, because I wasn't expecting it to fail, but, oh yeah, I know why. This is an example of what happens when it fails. So I generate a trace, which can be more or less complex. So this one is pretty complex. And then I have an unexpected output. What I was expecting is that I was expecting something with an error, and actually what I get is that the pet has been added. So the reason why I'm getting this unexpected error is that I forgot to rebuild that stuff. Yeah. But that's fine.
Never mind.
Never mind. Yeah. So the idea is that we have these two. What I would like to highlight in this here is that given the same model of things, right? We have the same thing. We are using the same model, which is totally pure, which is a pure abstract machine of what the interaction that we have. We are able to test the front end, and we are able to generate tests for the backend and validate whether or not the backend is actually passes actually it's actually valid with respect to our model. That's a part.
Yeah, so what we actually wanted to do is we wanted to show you what happens if we update our model. And somehow this got mixed up already. So we already demonstrated what happens if we update the model. We get an error. And the question is, shall we rewind this a little bit?
Or maybe we can just explain what's going on inside the code. So what it entails to fix the model, because basically I will just show you the code. So here is the reason we had this demo effect is that I forgot to recompile the code, to recompile the model. So this is the original model that we had, which with our two add pet, remove pet, the list pet input. What the rule we wanted to add was, what if I want to add a business rule which says, well, it is not, I mean, as a pet owner or as a customer, I'm not really interested in buying I'm not really interested in pets which don't have a name, right? So I want to be sure that when I add a pet to my store, then the pet has a name, right? So this is pretty simple. What I can do is I can just add some rule to my code. So this is all code, right? I can do whatever I want. But I can just say, OK, now I want to be sure that the pet name is not empty. So if it is empty, then, well, I expect to actually get. So I just send my error. So that's any rule. The question is, OK, given that rule, if I work with that rule with the front end, that's fine. The front end will hit the rule, and I will return an error, and the front end shall display the error, right? And so I can testing my front end against the mock, I can test that my front end actually reflects correctly the error. What's more interesting is, well, but what about the back end? What I need to do is I need to test the back end with an empty string. And this is where the generation part gets interesting, in that when you're actually generating tests, we all know that tests are finite, right? We cannot generate tests infinitely. We cannot test infinitely a system. So, and this is the famous Dijkstra quote about, testing can never prove can only prove the presence of bug, or disprove the presence of bug, but never prove the absence, because we can only run so many tests. So the idea is that when we generate the tests for the backend, we are controlling what we are doing, and that's where the magic happens. Is that we are restraining the domain of the test themselves, of what inputs we're generating, and so that's where we have the control. So we can control whatever we can use whatever rules we want and whatever kind of data we want. We can inject malformed data to verify, for example, the behavior is correct. We can generate invalid transitions, etc., etc. So that's really where the power comes from. So in this very simple example, what we do is that we are generating a simple list of pets, random list of pets, and a random list of remove and add, and we just check that they are what their effect is on the system. So the important thing is about these two double quotes, where we are adding something to the model that is generated to the backend. That's where we can actually check that our model fails.
Yes, and so maybe you can show the output again.
Yes.
So
yeah, that's
down
where
there you can see that there is there was an empty pet name somewhere in this list, and then.
So here we can see that we are generating input add pet with an empty pet name, which is a fish, and we expect the output to be that the pet name is empty with an error, but what we got is that the pet has been silently added by the backend.
Yeah, and so now we know our backend is not correct at the moment with respect to the specification, and now we need to fix our backend and implement this part there as well, this piece of business logic, and then everything will be fine again.
So, what's funny is that while we were preparing that talk, we were implementing the code or the model for that talk, and using that technique, we found bugs actually. So that's a true story. So for example, I found a bug with the roots. So the roots in the API, because the two are communicating with the API, the roots were incorrect in the code that I had written. So there was some overlap. And the model just told me, oh, I was expecting something, I didn't get it. What's wrong? And so another thing which was even more interesting is that when in a more advanced version that you will be able to delve into tomorrow if you come to our hands-on session, in the V2 version, I forgot in the actual implementation of the code, I forgot to empty, to remove, when a user logs out without buying the pets, we should put back the pets into the store because they should be able, other users should be able to buy it again. And I forgot to do that, and the model found it. And then there was even an error between the model in the model and the implementation where I was doing some copy pasting that led to remove pet was actually adding it. So something else that I found. So this is real. I mean, this is something we do for real, and this is just an application that I'm working on currently, which is a smart contract system, and we are doing just that. So we have defined a model of our system in pure code, really something that doesn't have any side effect. And what we are using to generate traces of execution that we send to our system, and our system is a pretty complicated distributed system, and check that the outputs are actually correct. And the whole model fits into maybe 100 or 150 lines of code, right? This is very compact. And all the rest is all the machinery, and a lot of details, of course, but all the machinery against the model. And what's really interesting is that you can also inject failures. What we are doing is that we have a model that injects failures in other components, and so we have traces of execution, say, okay, at this point, this component will fail, so we generate the failure, and we check that the actual system can repair or can have the expected output.
All right.
All right.
So, to wrap this up, we try to look at formal methods in combination with event sourcing or coding in general, and we actually think we found some interesting starting points here to actually make use of formal methods and to have it support our daily activities as developers. It seems to be quite an interesting approach to actually model the state machine of our internal state of the server and work with that. And then we can also use this to separate the development of the different parts of our system and make the parts independent in development, but still able to cooperate correctly. But there is, of course, a downside. There is no free lunch, as you probably all know. It takes time and energy to work on this model, to figure it out, to set it up, and to keep it up to date. That's like with everything. But on the other hand, it saves you the writing of quite a bunch of tests, which also costs energy. So pick your battles. All right. Yeah, as a bottom line takeaway, Dwight Eisenhower once said, plans are worthless, but planning is everything. And we would like to turn this into models are worthless, but modeling is everything. Thank you. Are there any questions?
I think we have a bit of time for questions. Insults, rotten tomatoes, whatever.
Rotten tomatoes.
What was the name of the tool that you drew from Quick something?
Quick Check.
Quick Check.
Quick Check. So Quick Check is a tool which was originally written in Haskell. There are now versions in nearly every language. There is even the inventors of Quick Check even run a successful company to test communication system in Erlang. And there are several tools. There are several Quick Check based tools to actually implement that kind of strategy. So implement the state machine model and generate traces out of the state machine model. Unfortunately, I know most of them are in Haskell, so that might be a bit of a hurdle to implement but the thing is that what we also wanted to show, and this is something we also wanted to practice tomorrow in the hands-on, is we don't care about the actual implementation language. What's important is that the model we have to write it, so it can be in any language, and then because we are interested in testing distributed system, most of the time we are testing with whatever protocol we are using. And nowadays, 95% of the time it's playing HTTP with REST and JSON. So the code you write to model in is not that relevant. So yeah, basically the generation is based on quick check. That's the bottom line.
Yeah. So I think we are out of time. Or what do you think?
We still have time for one question.
One is okay?
Is fine, yeah.
All right. Is there another one? There is one, I see.
So have you given any thought to continuous integration and continuous delivery? Because one of the beauty things about Pact was that you could literally take the Pact and put it in your testing part of your continuous delivery.
Yes.
Where your approach requires a more updated model at the time of pushing out your software.
The model is dynamic. I mean, just like, this is just another piece of the puzzle, right? And your contract should also be dynamic. So when your contract changes and you deploy your software, basically before deploying your software, you check, and you check that your software passes the contract, right? That's the idea of the consumer-driven contract testing. We are just doing the same, except that the model against which you are testing your software is a bit richer and tests more things. Obviously, it might be argued that it's a bit harder to write a dynamic model of the system or of your domain than to write specific examples, and that's probably true. On the other hand, what we wanted to highlight in this slide, the last slide of the talk, is that the effort you put into working on this model, even if it's something simpler, I mean, even working on the pet store or even working on basic interaction, whatever, the effort you put in this modeling, in being sure that it tests your various components, is actually worthwhile because you gain insights. I mean, it should be kind of obvious. I mean, this should be your domain model, right? Yeah. Like as in domain-driven design. And so this is something you invest in, and this is something that changes over time. Yes. So that's not a problem. That's not a bug. That's a feature changing over time, right? And it's an artifact like any other artifact. Yes. And you can hook this into your CI/CD chain, and what you saw before, the trace with the error at the end, that would be a failing test. Because it would then say, okay, the model, the backend doesn't fit the model. And then it fails and you need to fix it. I think we're out of time. We can take your question offline if you want, no problem. One other thing, Arnaud already mentioned this. Tomorrow morning, we are running a hands-on session. I have no idea whether there are any slots left. Our plan would be to give you this model as an executable thing. Either implement a front end or a back end against this model, and in the end we can just take all the front ends and back ends that you implemented and let them run against each other and see whether it actually works. And the method fulfills its promise. Thank you very much.
That's the idea. If you're interested, come join us tomorrow. Thank you.